Well, here we are. It's the physics video lecture. Physics 107B, video lecture 3. And we are working our way towards the full set of Maxwell's equations. And let's see what we had. We had Faraday's law last time. So we had, one that didn't work. We had Faraday's law and some interesting applications that led to it, and then the law itself. So we'll just write that we had this EMF minus the time derivative of the magnetic flux. And we turn that into a differential equation. So this was E dot dl when you integrated it, and so we ended up with eventually curl of E minus time derivative of the magnetic field. And a consequence of this, again, with that wheel, that wheel in the magnetic field, in the decreasing magnetic field, was that we found that the field is actually going to contain some angular momentum. So B field contains angular momentum. We already know that the E field has energy, so B field, I'll just write angular momentum. And as we make our way into the next chapter, we're going to find that the fields taken together have angular momentum, have linear momentum, have energy. So also, I'll put this parenthetically, linear momentum and energy. And that'll necessitate a deeper discussion of the conservation laws. Really interesting stuff. That'll be in the next chapter. Right now, we're going to continue with these concepts and make our way to the full Maxwell equations. A couple of examples with circuitry that'll give us a little handle on the idea of energy in the field and so forth. So what are we starting next? Inductance and self-inductance. So this is where the new topic for today starts. Inductance, self-inductance. And it shows up as a direct theoretical consequence if you just analyze a concrete circuit, the simplest circuit that you can imagine. So we have, so let's write, consider, we're going to imagine a circuit with a battery, a switch, and then a resistor. Here we go, home stretch, we've got a resistor. And we close the switch, and of course a current flows. But now we know about Faraday's law. The current that flows in this circuit when we close the switch, the red here closing the switch, the current that flows when we close the switch actually creates its own magnetic field by Ampere's law. Creates a magnetic field, it being a closed circuit. There's a flux. Therefore, there's a changing flux, and if there's a changing flux, there's an EMF associated with it, and it's not this one. It's going to oppose the change in flux. So let's write that down. So close the switch. Right, we can just kind of see the progression here. We close the switch. We're going to number these things. We're going to get the clockwise current I, okay, and we're going to get a magnetic flux because this current by the right-hand rule is producing B field, into the coil, into the loop there. So therefore we have changing magnetic flux, and therefore by Faraday's law we have opposing this EMF here. I'm going to call it E sub L minus d phi sub b dt opposing E sub 0 in the going to be a lot of these E sub 0s, not to, oh, can't see it, huh? Opposing E sub 0, not to be confused with epsilon 0. Okay, yeah, so that just comes about as a necessity. You know, when we do simple circuitry, we just imagine that we close the switch and we have a constant current. But of course, the current's going to start from 0, so it's not going to be instantaneous. And that's why we're going to have this change of flux. So now what we're going to do is introduce a new circuit element called the self-inductance, because we see even this circuit has that, so we're going to introduce a circuit element to take care of that property. And we're going to do it this way. Minus L di dt. Now the reason we can do this flux depends on the current, magnitude of the current, okay, as well as the B field. So we can go ahead and write it this way. Self-inductance and always, as always, check its units. Right, just solve for L, take the units. We've got volts in the numerator, and we've got the amperes per second. So in the denominator, so that's volts times seconds per ampere, and that is the Henry. Okay, so there's our unit, just in standard SI units. So what we do now is introduce that circuit element into this circuit since it's intrinsically there. So let's redraw the circuit. Circuit looks like this. We have our battery. We have this inductor. Okay, we have the switch as before, and we have the resistor as before. So what we're going to do is just run around this circuit with Kirchhoff's law and get a differential equation for it. And what we're going to find is how the current, the time behavior of the current. Okay. In other words, it's not going to start instantaneously, but it's going to go up to some constant value. In fact, the constant value it goes to will be the one just given by Ohm's law with the voltage and the resistance. Okay. But we'll get the time behavior of the current. So that's our next task. And let's go ahead and set up that differential equation. So we'll just do Kirchhoff's rule, going around that circuit diagram clockwise. Okay, so what does Kirchhoff say? We would have E0 minus, now the voltage drop across here is just going to be given by this L di dt. Okay, we close the switch. Okay, we close the switch. And then minus IR is going to be equal to 0. So this, we want to solve, find I of t. So we'll solve for di dt. Equals E0 minus IR divided by L equals E0 divided by L. Well, we can, hold on here. Yeah, better pull out the R over L. Okay. That's what it is. So let's do this. Pull out the R over L, that's going to be our time constant. So we'll have E0 over R minus I. That's nicer. Okay. So this way we can do our separation of variables and actually have our time or inverse time constant right there. Okay, so separation of variables, di E0 over R minus I is equal to R over L dt. Integrate, and the current starts at 0 and is going to end up at the whatever value of I it has. So this is an integration variable di prime, dt prime from 0 to t. Yes. And what do we have here? We'll have a minus from the interderivative there, minus natural log of E0 over R minus I. And then the lower boundary is 0, just E0 over R. And here we will have R over L times T. So we're just going to invert that and solve for I of t. Good, so we have exponential of both sides. Bring the minus sign to the right side. Exponential of both sides gives us 1 minus I divided by E0 over R is equal to E to the minus T over L over R. Put it this way because we have a time constant, and then we'll get I of T equals E0 over R times 1 minus E to the minus T over, I'm just going to write T over tau, because there's our time constant. T over tau, tau is equal to L over R. And you'll see this makes complete sense. Namely, if you graph this, which we'll do right under here, you've got a t-axis, you've got I, you can see the maximum value when time is sufficiently greater than the time constant is just given by the voltage over the resistance. So that's just by Ohm's law. So you've got I max equals E0 over R. So that's going to be an asymptotic value, and we're just going to grow linearly initially, and then it saturates at some point. So yeah, 1 over E here, so your tau is out here somewhere. And that's the behavior. So the final result of this thing with the current flowing through here is that there's power going to the resistor, but we're going to see some work had to actually be done to charge up this self-inductance, this inductor. But the power dissipation, energy dissipation, is still due to the resistor. It gets hot. Here you're going to store up energy, as we're going to see later, in the field. But once you reach that steady state, you've just got the current flowing, and then the circuit just behaves like the simple circuit the way we used to have them without the inductance. Okay. Then it's just Ohm's law, constant current. So this is the phase when it starts up, and this is when it's saturated. Good. And so you can see what the effect of this circuit element is. It keeps the current from just jumping up to the full value right away. Okay? It eases up into it. Okay, let's see what's next. What's next is we're going to calculate self-inductance for such a circuit element. In fact, for an actual coil of loops of wire. And having calculated that, we'll be able to relate it to the energy stored in the magnetic field. So those are our two goals. Okay. So the comment here that I just stated, inductance keeps the current from jumping to its maximum value immediately. Jumping there right away. And now we're going to analyze the situation once again. We could even think of this analysis as being without that circuit element and just with the loop once again. Point now to be made. So we had its definition. This is just from Faraday's law. So minus L di dt. That was the new circuit element that we'd introduced. Of course, this was just minus d phi dt. And what we can see is that we're going to have this flux let me write this down first, and then we'll discuss that. We've got a flux that depends on both these quantities, okay? L and I. We have proportionality for both of them. Because clearly from here, if L is a constant, the flux depends on di dt, therefore it's the same derivative. So the flux depends on I. And of course, since L is a constant, we could take this L times I into the phi. Di dt. So the flux is L times I. So that's clear. And we'll use this. So I'll complete the sentence. We have this, so that this expression here can be used to calculate the self-inductance. Calculate L. So this is an interesting example. What we're going to do is imagine we have a solenoid, so many turns, okay. And this thing has a length L, a cross-sectional area A, length L, cross-sectional area A, and N turns. Okay. So we can say lowercase n is just going to be this number of turns divided by L, but of course it can also be the number of turns per unit length if we want. Okay. And what we want to do is figure out L for this object here. And I think I have to stipulate also the radius, but I need a different radius. So I'm going to use lowercase r. So r, here we go. A equals pi r squared, and r is much less than L. So that's what we'll work with. What we do next is we just turn that thing into a torus. So we'll say next, fashion a torus out of this thing, and so the torus is like that. Maybe I should do a, well, need to be a little bit better about the torus here, so let's imagine that I've, there we go, bent it around here. Okay. And because of these conditions, what's going to happen down here is not materially different than what's going on up there. They are much less than L. So now I'm going to take a circle right down the middle of radius 2 of circumference 2 pi capital R. On the other hand, I have these currents piercing the inner surface there n times, okay, because there's n turns. So here's what we get. Write down Ampere's law. We have the integral B dot dl along my red curve there is going to be equal to the u naught I enclosed. And so here, by the symmetry of this thing, we're just going to have the field curving around inside here. So we'll just have B times 2 pi r capital R. And on the right side, we're just going to have mu naught, and then n times I, because we're piercing that n times. So n times I, u naught capital N I, for the field, I'll just divide here, so I'll have mu naught n over 2 pi r, but this 2 pi r is really just the same as this original L up there, because I turned the thing into a torus, so I have mu naught n over L, and of course I have the current there, times I as well. So now we can go into the L. So now L is equal to phi divided by I. Right, from up there, that's going to get rid of this I right there when I divide by it. And so I'm going to still write it down. Let me go ahead and write it down anyway. So I have n mu naught n a. I had the I and the I canceled. So that would be mu naught n squared, and I'll divide by the L there. A over L. Okay, so that's pretty good, right? So this is the inductance of this thing here, right? In order to do the transformation from a straight thing to a torus here, you have to have sufficiently large n for this to really make sense. Okay, but in that case, mu naught n squared cross-sectional area divided by the length. So we're talking about the inductance of this object right here. Good. So the next thing, now that we have this expression, we're going to talk about, we don't have to actually have to use this one in particular, but you see we have an inductance from an object here. We're going to talk about how much energy is in the field of this thing, how much energy is stored after it's been, after the current has gone from 0 to the full value. Okay. So this we will call, and maybe I should, I'll just put this here right next to this note so that it's together. Result L is equal to mu naught n squared cross-sectional area over the length. That's good. Okay, so our next goal here is to get the energy in the magnetic field. And the energy in the magnetic field that's stored in here, respectively, up in there. So energy in magnetic fields is our topic. And the circuit's no longer up there, but so work is done as our circuit for it as the current begins to flow. And the circuit I'm talking about again is this one right here. So let's keep it picture here. So we had inductor, we had the switch, and we had the resistor. L, R. Okay, and then we close the switch. And there's two types of work being done. This one here, this resistor, is associated with power, energy dissipation, production of heat. Okay, and that will constantly be happening, but there is work being done against that opposing EMF that we get due to Faraday's law and the self-inductance. Okay, so that work we can think of as being stored in the field. Okay, it's being done. It's not an energy dissipation as it is with the resistor. So that's what we're talking about. So work's being done, flow. So first kind is that energy is being dissipated. And that's in our resistor. And the second kind, we can say energy is being stored. Because since it's not being dissipated, and definitely there's work being done against that EMF, it has to be recoverable. That's the idea. So if I say it's being stored, it must somehow be recoverable. So the first half of this is actually pretty basic now. We have power equals work that's being done, and voltage times current, and that would be L I E I T. Okay, just by substitution. There's the current minus L d I dt cancels out. So if we integrate this, zero to t, on the one hand we do that here, we have integral L out here, I di dt. Okay, you can cancel those, and you're just going from 0 to W. So there's your W. Here you're going from 0 to T. DI's cancel. You're just going to get I squared over 2. Okay. So we have work is equal to 1/2 L I squared. So there's our expression. And this is after the full current is flowing. So we already know that this I of t comes up with that exponential function, but after it reaches the full amount, that's how much work has been done. The details don't matter because of the cancellation of the dt's there. The actual details of the function. So it's 1/2 L I squared, and we're going to transform that to get the same expression in terms of the energy stored in the magnetic field. Okay. Right now, we have the inductance, we have the final current, and that's how much energy is stored. But we want to actually express it in terms of the magnetic field itself. So let's call this star here. Say next, let's express this in terms of energy stored in the magnetic field. So that'll take a few steps. So next, W, right, star. Terms of the B field. So let's see. We'll begin with the flux L times I on the one hand. On the other hand, it's just Faraday's law again. B dot D area. I'm using lowercase a for area because there's a lot of other uppercase a's. Surface, and B is the curl of the vector potential. I'm going to dot that into dA, and I can express that using Stokes' theorem as the line integral along the boundary of my surface A dot dl, like that. Okay. So that's the flux. And then we're going to go ahead and use that expression right there. So we'll have the work, which is what we're looking for. We've got the 1/2. I'm going to pull out an I and an L times I. L I squared, because the L times I we have right here. So 1/2 I, L times I, we're going to take this, integral A dot dl, okay, along a curve. And we can take this into the integral, and then it'll just be the direction of our current. So if we take this into the integral, we can also say we have a 1/2 integral A dot I dl without the vector on it. Okay, so that's equivalent. And this we want to generalize now to a volume. So I'll go ahead and write it this way. I dl is going to generalize to J d volume. Okay, because we have a current times a length. Here we'd have a current divided by an area times a volume, so that is dimensionally also a current times a length. So we're going to turn this integral into a volume integral. So just right here, generalize. Generalizing, what's a G? And so yeah, we'll rewrite this integral in terms of this generalization. By the way, that was a vector, sorry. And we have W energy, does that work? We have 1/2 integral A dot J d tau for volume element. So this is what we're going to work on next. So we have to eliminate the vector potential. Okay, eliminate the vector potential. So here we have some well, we know B is equal to the curl of the vector potential. So what we're going to do is the following. Use curl of B is equal to mu naught J, and use, coming out of this, A dot J is equal to 1 over mu naught A dot curl of B. So we plug that in to here. So now we have an A dot J, and a product rule. So the divergence A cross B is equal to B dot curl of A minus A dot curl of B. So there's a product rule as your list of many differentiation rules. And these we can now put together into this integral expression here. So let's see what we have. Now, this W is going to be the 1/2 Okay, yeah, before I do that, you can see where I have A dot curl of B, A dot curl of B, okay? So that's going to be this minus this one, so B dot curl of A minus this divergence expression right here. So we get 1/2 mu naught integral B squared d tau minus 1/2 mu naught. Let me just write this volume. Maybe I should have not skipped this step. B volume A cross B dot D area. Okay, so I skipped this step, but we can easily reconstruct. Okay. So again, A dot J, we have that right here. So this 1/2 mu naught A dot curl of B, that's right here. A dot curl of B, and that's these two expressions. Okay, so it's B dot curl of A minus divergence A cross B. The B dot curl of A, do the work right here, that's B dotted with itself. Okay. So since I'm integrating over a volume, which I didn't have here yet, okay, integrating over a volume, that's 1/2 mu naught, okay, B squared d tau. Okay. The other one was the divergence of A cross B, and we just used Gauss's integral theorem right here and turned it into the surface area. So if that's that volume, that's the surface bounding the volume, that's a flux integral with A dot B, and you're saying, well, we haven't gotten rid of A yet, but what we're finally going to do is take the limit of the volume and encompassing all of space. So the limit of all of space, we're just going to remain with this integral here, and we'll have to argue that this one vanishes as the boundaries of, say, the sphere of radius r goes to infinity. So yeah, actually we didn't skip a single step. Now we have everything here, all the ingredients, plug these ingredients into here, and for this one, we did Gauss's law, Gauss's integral theorem, okay, the divergence theorem. So what we're going to finally do is take the limit. So finally, limit all of space, and then we just have 1/2 mu naught B squared B volume, and this one is going to vanish. Plus 0, comma, because, and we could just estimate this integral. Okay. So if we estimate, we'll do it right here. We estimate A cross B dotted into dA. That's going to be, I'm just going to write integral A, B, dA. So we've gotten rid of all the dot products. Okay, we just have magnitudes. And this goes as 1/r squared. It's E field at great distances, B sub r law, for instance. since the curl of A is equal to B, that is to say the derivative of A is equal to B, this one must go as 1 over R. Okay? So we've got a 1 over R cubed. The surface area of a sphere of radius R goes as R squared. Okay. So we've got R squared over R cubed, and that goes to 0 as R goes to infinity. So yeah, this boundary term vanishes, and we have this very nice and simple expression. And we can even see we've got a B squared over 2 mu naught for an energy density, and we'd seen something previously where we had E squared over epsilon naught as an energy density. So yeah, it comes out looking good. I'm going to consult the clock here. Okay, so we can see energy stored in the field. This, for example, could have been the energy stored in that long solenoid. Okay? In which case, just to mention that, a good example. In the case of the solenoid, the field is only inside the solenoid. Especially in the limiting case, got some edge effects outside the solenoid, no field at all. So it's just going to be B squared inside the solenoid times the volume of the solenoid. Okay. Yeah, that would actually be a good one to pay attention to as a consistency check. Okay. Volume integral B squared in the solenoid, it literally is the volume inside the solenoid. And yeah, the B field just vanishes outside the solenoid. So it doesn't matter if you're integrating over all of space. Okay, let's see what we have left here. So now we're ready to write up Maxwell's equations. And so if we put the final touch with, the missing link, so to speak, for the full Maxwell's equations. So let's go ahead and write them down. So the differential equation form of the laws of electricity and magnetism. So laws of electricity and magnetism, we have divergence of E equals rho over epsilon naught. Gauss's law, and in particular, you'll get Coulomb's law out of this for point charge. Okay. So I'll just put here Gauss and also Coulomb's law. We have right there. Divergence of B equals 0. We have no magnetic monopoles. We can't isolate magnetic charge. We have the curl of E equals minus dB dt, so there's Faraday's law. And then we have Ampere's law. Curl of B is equal to mu naught J. So we have these 4 laws. So we could write no magnetic monopole here. Monopole. Now, it's just a fact of vector calculus that the divergence of a curl vanishes identically. So note here, divergence of a curl vanishes. Okay. So if we apply that to this third equation right here, you could say, I number these 1, 2, 3, and 4. 1, 2, 3, 4. Okay. So we take the third equation and do the divergence of it. So we have div curl of E. And on the right side, we have minus d dt div B. Okay. We generally assume we can interchange derivatives. Okay. So good, this is identically equal to 0, and divergence of B is identically equal to 0. So that checks out. If we do the same thing on Ampere's law, we get divergence curl of B equals mu naught divergence of J. And here we actually run into a problem because this is identically equal to 0 just by the laws of mathematics. On the other hand, this does not have to be 0. Okay. When is it 0? Okay. Well, we can say the divergence of J is 0 when J is equal to constant, uniform. Okay. So note, divergence of J equals 0 when J is constant, but the current density doesn't have to be constant. In fact, but from continuity, which is really fundamental after all, from the continuity equation, we knew that we had d rho dt equals minus divergence of J. So divergence of J not being equal to 0 just means that rho is not constant time. and you know, density in space as well, because this is a flow. So this is the conundrum that we would face up to. We would have to face when we have these equations of motion. And we can say this was before Maxwell did his analysis on this. And the analysis is going to be done right here, okay, with the divergence of J. So yeah, that's the last thing we're going to do right now. So we have to fix this problem, and we're just going to start, literally, we're going to start here with the, it's all up on the board here. We're just going to start with the continuity equation. Remember, the continuity equation just expresses conservation of charge. So that's as fundamental as anything in electricity and magnetism, conservation of charge. So here's what we do. We're going to take the divergence of J equals minus d rho dt, and then express this in terms of the density right there, because that's the same charge density we're talking about. Okay. So what do we have? We have minus d over dt, and we can just take the charge density epsilon naught, which is a natural constant, divergence of E. So we can just go ahead and do this, minus epsilon naught, or in fact, let's do this. Since we have constants here, we can just have equals divergence of minus epsilon naught d e dt. And where we have a mu naught j, what we're going to do is add a mu naught times this thing here to our current. And that's all we have to do. So replace equation 4 with the following curl of B equals U naught J plus, or U naught epsilon naught dE dt. And this will be the Ampere Maxwell equation. Yeah. So I'll go ahead and put a box around here. Ampere Maxwell. So the thing is, we had this conundrum here. Now if we take the curl, if we take the divergence of the left side, that's 0. The divergence of this right side is also equal to 0. That's what we needed, because the divergence of this is going to be just equal to that right there by this. Okay. That's why I had a minus sign there. That's why I added it as a plus sign. Okay, so when I take that divergence, I get the minus mu naught J. Good, and this is called the displacement current. So this is where we'll leave it. Okay, we have all the ingredients in place. Still have a fair amount to do, but we have 1, 2, 3, 4. I call this 4 as well. I can call it 4 prime. Those are the 4 equations that it's interesting. This is just it's just an invention, but it's a consistent invention with everything else. So it really had to be there. I think that's where we'll leave it. The displacement current is this part here, because the mu naught is pulled out front. Current density, this is supposed to be a vector. And this here is the displacement current. So yeah, what we'll do next time is investigate this a little bit more. There's a really clean way to visualize this literally using a parallel plate capacitor. And we're going to have to do a number of things. We're eventually headed for electromagnetic waves. And in fact, electromagnetic waves in vacuum, this term is gone, and then these equations look very symmetric indeed. And we will see, we'll see all of that. So for now, let me just write up a homework number 2, problems similar to what we were talking about today. And what do I have here? So chapter 7. (18, 25, 27). 18, 25, 27. That's a 7. 30 and 31. Okay, good. We'll see you guys next time.